it's about the basic structure of a PC as well as power and setup. So today we're going to talk about power supplies. We're going to introduce another topic first before we really get into power and power supplies. This chapter is technically about electricity and power supplies, but it introduces something called form factor first, and that's kind of what we're going to go over first. Because form factor is the size, shape, and general makeup of any hardware component. And PCs in general, and motherboards in particular, have a specific form factor. And so it's kind of like when we talk about form factor, kind of talking about that, you know, you can't take a Lamborghini and throw a Ford 1500 engine into it, okay? The Lamborghini has a form factor. It has a general size and shape, and only certain things will go in it that are made to go in that Lamborghini. Or if you've got a Chevy and your dad's got a Ford, it doesn't, just because they both drive and they're both 1500 pickups, it doesn't mean you can take the engine out of one and stick it in the other. Okay? The form factor determines what parts can go in it. Okay? So the form factor determines the general size, shape, makeup of a hardware component, and the form factor of a PC determines what things go in it and what things will work in it. Okay? So the big things that have to match up, your case, different color, your case has to match the motherboard in order for it to even screw in. Okay? When I get a motherboard, it has very specific holes in it that let it line up and screw into a case. And when I get this motherboard, if those screws don't line up with the holes, you see the holes in the bottom of the motherboard? If those holes don't line up, do you need a pen? Huh? No? Yes? So if those holes don't line up that I see in the bottom of the motherboard in the case, I obviously can't screw it in. Just like you can't fit a Ford engine in a Chevy. You can't do a lot of work, I don't know. But anyway, the holes have to line up. That's part of the form factor of the motherboard. And then the power supply has to do the same thing. It has to line up, it has to be able to screw into the case, and it has to be able to plug into the motherboard. I've got a box of power supplies right here. Now I have a power supply somewhere right there. These look anything alike. The plugs are the same. This power supply actually would power the same one as this motherboard, except for the fact that I could never screw this into the same case that I could screw this one into. Okay? So things have to line up. That's part of the form factor that has to line up. Okay? Generally, the motherboard drives the decision. We've decided what we want to make, and that's why the first chapter that we actually decide stuff on is the motherboards. We decide what we're going to make, what kind of PC we're going to build, and then we have to buy all the other components to work around it. Okay? If you buy this motherboard, just set it down. If I buy this motherboard and this happens to be the one I have, then I obviously have to buy a case that this fits into, and then a power supply that fits in the case and plugs in the motherboard. So all the decisions kind of spread out from the motherboard. Okay, which is the first real component we're going to do. And deciding what motherboard we have and the form factor determines what we're going to be able to do with that system. Okay, if we build the smallest PC, micro ATX machine that's that big, never going to make it a gamer machine, right? We're never going to be able to fit a video card into it. So these things all continue on. Now, when we match those things up, I already said this, the motherboard has to fit the case, the power supply has to fit the case and the motherboard, and provide the correct voltage, which is one of the subjects of this chapter, okay, is determining that. Because if we just have one that plugs in but doesn't give us the right actually wattage or total power, then it's not going to turn on. If it does turn on, it's going to shut itself off. So we have to make sure we determine the right components. I already said this, the holes have to align with the case. Holes in the case have to align with the ports in the motherboard, meaning the back. I can't put this into this. It won't fit. I can't put this into that. I can't put this into this because the kind of case it is. This would line up with that, and my ports are on the same side. And this piece right here, and this case pops out. So it comes with this little cover plate, and so it goes over that and makes all those ports line up too. So there are some things sometimes that you might get a case and think, hey, I could use that one, like this one, which you cannot use for any motherboard other than the one that came with that one, because Dell makes this plate part of the case, so you can't use it for anything else. So all those holes in the case have to line up with the motherboard. And then you have to make sure you could hook up the switches to make the front panel connectors to make it work. And this motherboard, it has very generic wires that come out from the front, and they plug in to specific spots on this motherboard. And I can go and unplug this wire, and I can plug it in differently for a different motherboard. I can move all those wires around. This isn't like one big block. This is down here. Down here. All these are separate, so I can pull all these pairs out and plug them in a different spot on a different motherboard. Okay? And they go in this particular motherboard. They go in right there, and then you just have to plug in the right pair. Which is one of the harder things when people build their first PC. They don't understand how to make those buttons and wires work so that when I push the power button, it turns on the power. Because if I get the wrong one, I can make the power button work the LED light and it doesn't do anything. So you have to make sure all the things here, because I've got a power button, I got a power light, I got a hard drive light, I got a reset button. Usually I have 4 things in the front of a PC that hook up, those being power and reset switches, and power and hard drive lights, and they plug in exactly the same. So if you don't put them over the right holes, they don't. So I have to make sure that I've got those plugs that fit and hook up. This one has just one big plug. Just go boom. If I look at the ones that you guys were pulling drives and stuff out of the other day, this Dell right here. This just has one big cable that plugs in. If I can find it, right here. Actually, you can almost not even see it. This big, huge cable all plugs in together, and that works all the front panel switches, USB, everything. So you would not be able to use this one somewhere else. Same thing with this. This back panel doesn't come out, so you wouldn't be able to use this case for something else. Okay. So they make their stuff very proprietary and very unupgradable, and that goes bad unless you can buy the exact same motherboard from Dell, which is, I think, one of the marketing strategies. There's a bunch of different form factors out there. Baby AT has gone away. The only 2 we have in this school are called ATX and VTX. Okay, those are the main form factors out there. And of the form factors that are out there, ATX is the one we're going to use for every single one of our projects because it is the most prevalent one. Okay, these other ones are very proprietary, specific motherboard form factors. So we're going to be doing almost everything with ATX, although I want you to know that VTX is out there in the school. This one's VTX, that one's ATX. All the parts are interchangeable except for the motherboard and the case, okay? I could pull the CPU from this one and put it in another computer. I could pull any of the memory, hard drive, everything out except for the case itself and the motherboard. Can you see what the difference is between those 2? They're exact mirror images of each other. You have them butt to butt, they look the same, okay? VTX is backwards of ATX. If I look at the back of the computer, motherboard's on the opposite side. makes a difference. I can't stick a BTX motherboard in an ATX case. Even if this did have a pop-out plate cover, I wouldn't be able to put it in there. The power supply works the same, screws in the same, plugs in the same, holes are lined up exactly the same. If I look, it's back, it's flipped over though. See how these two are the same place as those? Oh, these two are the same place as those two. These two are the, I can swap these power supplies just fine. Okay? But the motherboards I can't, cases I can't, because they're exactly flipped versions of each other. BTX was an attempt to change the motherboard to a new form factor. It basically failed. Dell still uses it, obviously, but most other places don't. Most places, whenever you look, you're going to find ATX. But like I said, I could put this ATX CPU in a BTX motherboard. I could put the fan in there. Every other component other than the motherboard would ever screw into the case. So these are the two that we see here at school, and ATX is the one you're going to use for every single one of your projects. So when you go to buy your case, it needs to be an ATX case. When you need to go buy your motherboard, it needs to be an ATX motherboard. And then from then on out, it's not going to make that much of a difference. Okay? So when we look at motherboards, we need to know the general size, shape, and makeup of the components. And we're going to spend a lot more time in Chapter 4 on this. They have different kind of power plugs. This is the older AT power plug. All the ones we have now are these 20/24 pin. That is a Chapter 3 thing. Power supply, which means they could have 20, they could have 24. When you buy a new one, most of them are 24. I gotta grab a new power supply real fast here to show you what I'm talking about. Most of the new motherboards are 24, some of them are still 20, and if you buy a power supply that says it's 20/24, what it means is that it's 24, and it's got 4 pins that slide off. I've had people return power supplies before because they said the power was too big, and it would fit, it just slides off. Okay, so if it's too small, look for the little connector, now I can make it slide back on. Okay, so it's 20 or 24 pins on the power supply. Okay, but that's what it looks like. It's got a little clip. When it plugs into the motherboard, it snaps down. Most motherboards today, I'm going to say all motherboards today, actually have 2 power connectors. They have the main P, it's called the P1 plug, which in this one is right there. You would plug in, and it has a little snap, this way. It has the main P1 plug, and it also has a P4 plug, and depending on the motherboard, it might just have a 4-pin or could have an 8-pin plug in there. If both of these are not plugged on, this motherboard will not come on. Like you see light spit on it, okay? Because this one's powering the motherboard, and this one's providing the extra power to the CPU. So without this, the CPU fails its check. It doesn't come on, so you see a light but no beeps, no nothing. Okay? So very often, if you see it acts like it's starting to come on, but it doesn't come on all the way, it could be this one's unseated or not plugged in all the way. Pretty easy to do. We're going to test some power supplies in this chapter. You're going to learn how to test them. It used to be, before I had a power supply tester, that it was pretty much of a pain. You grab another power supply and try another one. But anymore, I have these power supply testers that we just plug into the power supply to check if it's good. If you're starting with a computer and won't turn on at all, the first thing I always check is the power supply, because it really stinks. You waste a whole lot of time troubleshooting all kinds of junk, right away because your power supply, you didn't check it first. So it's just one big plug and one little plug to plug a power supply in. The ATX form factor came out in 1995. That's why they tried to change it, because they wanted to upgrade it, but it turns out they didn't need to upgrade it. The holes were lined up fine, and we've stuck with it for a long time. I'm not going to ask you what the shape its size is, because there are a whole bunch of different sizes. That was the main one. They moved in the ATX the CPU and the memory slots. All ATXs are basically designed the exact same. Ouch, that hurt. Where it goes back panel CPU memory. Okay, so they all go back panel CPU memory, and then all the slots are moved over to the side. so that if you used a really long card, nothing was in the way. So the difference between different motherboards is how far out this goes and how many expansion slots on it. They all go back panel, CPU, on an ATX motherboard. So if I grabbed it, if I grabbed a different one, I get some pictures up here. Basically, they follow the same thing. Power supply motherboard uses a single P1 connector, and then we added another connector on there for the CPU using more power. And the power supply in an ATX motherboard always blows the air out of the case. Okay, which is important to know that if your power supply is in the back like this one, the air is going out this way, so it has an airflow that's supposed to happen. What's supposed to happen is the air gets pulled in the front and goes out the back. So if you add another fan like this one, and you add it wrong, where it's blowing in instead of blowing out, you just interrupted the airflow. And I've had people do that before their computers overheat because it's blowing out, holding hot air right here, and it's sucking in the hot air right there. It's supposed to be pulling it all out the back. And this one was overheating because apparently Mr. Poole will blame me, put the CPU fan in backwards. This should be going the other way. This is actually blowing this way. Now there's no arrows on there. You have to know how to look at a fan to know. So that's going that way. It's doing the exact opposite. So Cindy's computer kept overheating. And it was running so hot because this was trying to blow out, but it was blowing all the biggest heat in the computer and the CPU. It was blowing it back in all the time. So it was, if this was flipped the other way, then all the air would have been going out the back. But that's one of the things about ATX. The power supply always blows air out of the case by definition on an ATX motherboard. ATXs basically look like this. They all have back panel, CPU of some sort, then memory, and then all their expansion slots are defined down here, and they can get bigger and bigger out that way, or smaller and smaller. The different sizes, you've got, this is sizes, we got Pico, ETX, Epic, they're all ATX, okay? And we have, here's the size of a micro, and then we go to a regular ATX, and then we can get it extended up. I'm just telling you that the layout's the same. When they say micro, or mini, or extended, they're just expanding on the basic size and where the screw holes started, okay? Right here. So they're going to have those four, and then maybe they'll have these, and maybe they'll have more here as they expand the motherboard out. This isn't the picture I was looking for, but it's close to what I was looking for. But you can see that as we get from a smaller to a larger one, we still use these basic holes, and now as I get to a bigger board, I use more holes to screw down into the PC, okay? If you buy a micro ATX case and a regular ATX motherboard, it will not fit, right? The motherboard can be bigger than the case. However, if you get a full-sized ATX case, any ATX will fit inside it. You just won't use all the screws. This one's a full-size ATX, that one's a full-size BTX. You can see this one, how much smaller this one is. And this one, I wouldn't use any of that extended area motherboard. It would still fit inside. So that's basic form factor. So ATX is probably a new term that you guys didn't know. When we're looking at stuff, we're looking for ATX form factor stuff, okay? Not BTX. This is very proprietary and only very specific manufacturers use it. We're not trying to make a Dell PC in this class. We're trying to make a Nix PC in this class, okay? Okay, so again, this is the basic layout. I have my back panel. I have some kind of CPU socket, and I have some number of memory slots, which can be anywhere between 2 and 8, really. 8 being a really super PC, 4 being a nice PC, 2 being a chintzy PC. Okay? I only had 2 slots, I'm not going to be able to fit much memory in there. This one's got 4, only 2 are being used. That one's got 4, only 2 are being used. This one's got 4, so none are being used. The colors indicate that the memory goes together, so if I was to put in 2 sticks, I'd put them in the 2 blue or the 2 black. I wouldn't put them in black and blue, because that won't work as well. It will work, but it won't work as well. If you didn't know that when you were looking at this. Okay? So that's the basics. Question on that? I don't think I have my speakers on. I'll do that. In our AC. Anyway, so we're going to start talking about power now because that's really the subject of this section. I don't have my pen. There we go. I'm supposed to name the band. No one wants to name the band? Okay, so anyway, we're talking about AC/DC today, specifically about electricity, and defining what the different kinds of electricity are that we use in a PC, and how those things are changed and affected, okay? So you need to understand what alternating current is and what direct current is. AC current is the kind that comes out of our wall, okay? It's the most efficient method of transmission, which is why it's what comes out of our wall. It's why that's what's sent over power lines, okay? AC current cycles back and forth at a rate of 60 hertz or 60 cycles per second. And in our currency, right, we get 110 volt. Alternating current is what comes out of our electric file. Okay, we have 110 volt AC that comes out of our electric outlets. We get it because it's the most efficient way to send it, but it's not what electrical components want to use. Specifically, small, very delicate electrical components don't like alternating current. The only electrical components I've ever had in my life that use alternating are airplanes, because the circuit is the size of a 300,000-pound airplane. It has to transmit all the way from the cockpit all the way to the back, so it uses three-phase AC current for a lot of the electrical components in an airplane. But most electrical components use DC power. Okay? Oh, did I not go to DC? I didn't go to DC. Why didn't I go? Maybe I'm going to go to the AC. I don't have that on the slide. I apparently erased it down there. I don't know why. I'm going to go ahead and, I'm sure it's on a slide later. So DC stands for direct current. Okay? It does not alternate at all. It's a very flat, steady current. Okay? And what small electrical components need. And we have to turn our AC into DC inside a PC. There's some measures and properties of electricity that we need to understand, those being volt, amp, and watt. Okay? Volt is your potential. Okay? Amp is your flow. I'm going to redefine these again. And watt is your total power. I'm going to give you some ways to remember this. Okay? And ohms are resistance. I'm going to tell you we're not going to deal with ohms. So I don't really care if this ohms calculate anything when we talk about electricity. Okay? So we're going to look at those three things here as we go along. So when we look at volts, it's the potential difference in the circuit. Okay? So it means that you could pull that much out of the circuit. Okay? Amps is the current flowing through the circuit, and then wattage is the total power. And I have a little way that I like to explain it to you. Okay, so when we look at water, okay, we have a specific size of pipe running through our house, and that size of the pipe is what I want you to think of as voltage. Okay. The size of the pipe has nothing to do with the amount of water that's coming out when there's no water flow. Right? If I don't have the water turned on, the size of the pipe does nothing. There's no flow. Okay? Then amps is the flow, or how much you turn on the spigot. Okay? How fast the water is going through it. Amps is how fast the water is going through the pipe. So the amount of water we would get out that come out into our bucket, and pretend that's water, would be defined by how big the pipe is, and how much we turn on the hose, or how fast the flow is going. Okay, so watts is total power is defined by volts times amps, just like if we were getting water through a pipe in our house, it would be defined by the size of the pipe, the volume of the pipe, by the flow of water that is going through the pipe, would be how much water we would get out. And with electricity, the voltage times the flow of electricity, or the ampage, equals the total amount of power that comes out of the pipe. Okay? So you need to understand those three terms and how they are defined. Volts times amps equals watts. So the potential for electricity multiplied by the flow of the electricity equals the total amount of electricity coming out. Okay? Every power supply is defined by a very specific wattage. It can only handle so much flow. So if I look this one, I look on the box, it says it's a 400 watt power supply. It can't handle a flow of any, that's maximum. It can't handle a flow of total power of any more than 400 watts. So if I have a bunch of things requiring specific voltages, and it goes over that, either the computer doesn't work, or things don't work intermittently, or the thing turns off, but it doesn't work right. Okay? And one of the hardest parts of this chapter, guys are trying to figure out what wattage we need on a PC, but it's one of the most important things in this chapter because this is not an expensive part. It can be. You can pay a lot for a power supply. You can also pay $15 for a power supply. This one's obviously dusty. So you pick the right one the first time and you put the right one in, you're going to be way ahead. It makes things last longer. So volts times amps equals watts. Volts is the potential, amps is the current amount of electricity flowing through, and wattage is the total power, which is calculated by volts times amps. Okay, wow, we popped right past the rest of that section on this slideshow thing. Okay, so as I'm looking at, I'm going to do just to show you what I'm talking about. Watts is total power. How much power a power supply unit, when I write PSU, that's what I'm saying, a power supply can put out is determined by a definite, it can only put out so much power, total power. And then it has components that need that power. For instance, a hard drive has a specific plug that it uses, and it's this plug. 12-volt plug. Okay, so that hard drive pulls 12 volts. Yeah.
I have a student that like backlights out or something on the screen. Can they come down to you?
During intervention, I've got a class right now.
Okay, thanks.
Okay, so hard drives pull or use a 12-volt plug. Okay, and a hard drive may use 3 amps. Okay, that's the maximum current. When we say how many amps, that's the maximum it's going to pull. In other words, when a hard drive is spinning up, it's going to use 3 amps of current, and then once it's running, it probably drops down to 2. Okay. So how many watts can a hard drive pull? 36. Okay. So a hard drive might pull as much as 36 watts. That's one component on our PC. So when we go through a PC, we have to go through each component and figure out what the maximum it can pull. Not the average, because we need to know maximum, because when we turn on our PC, everything's pulling maximum. If we can't handle the maximum of everything at one time, PC won't start running. Okay? So we add all those things together, and then we have to stay under whatever the total power is. For instance, that one happens to be 400 watts. We have to stay under that, or our PC won't work. And we're going to learn how to calculate all those different things calculate that. But I wanted you to understand that each component has a specific voltage, and it will pull so many amps. So that component has so much watts or so much total power, and then we have to make sure we stay underneath the total power of the power supply. Okay, static electricity is one of the other electrical things in this chapter. Okay, static electricity. If anybody have a little sister, they go around the carpet like that, and shock them in the wintertime. Big sister, they go around and shock in the wintertime. Okay, I had a little sister, so we had a carpeted house, and every winter, Tracy would be screaming. I was a mean neighbor. So static electricity is the leveling out of potential power between, or potential voltage between you and something else. You built up power, electricity inside you, then when you touch something else, it dissipates and it equals out. Okay? So when I touch Billy, we're now at the same potential. We just went, yeah. If I had any static electricity, it went into him or vice versa. Okay? Static electricity is something that ruins PCs all the time. Okay? And it ruins PCs because if I don't handle electrical components correctly, I can easily dissipate static electricity into this, possibly without even knowing it, and ruining parts of the computer. Whenever we work inside a PC, we always unplug it first. We hold down the power button for 20 seconds to dissipate any power that's inside the motherboard and a capacitor, and we always touch the power supply. The power supply is screwed in and connected to everything in the PC, right? They're all wired together. And that's the hardiest component in this PC. So we always start by touching the power supply. Now I can work inside the PC. If I walk away and come back, the first thing I do is touch the power supply again. If I'm standing there for a long time and somebody walks up and touches me, did my static electricity just change? It did. Touch the power supply again. If I grab something else, touch the power supply again. Whenever I'm working inside a PC, I'm doing that all the time. Okay, so it can ruin PCs because we dissipate electricity into them, so we need to make sure we always touch the power supply before we get into it. Some numbers that you need to remember, which you guys don't know yet. The voltage to even know that you discharged electricity is 3,000 volts. If you haven't discharged 3,000 volts, you don't even know it. Okay? Don't even know it. So I can discharge 2,000 volts into this, never feel it at all. Okay? To hear it, to hear the crack when you touch your sister, it's 6,000 volts to hear it. And to see it, it's 8,000 volts. That's how much you discharged into something. If you actually saw spark when you touch something, it was 8,000 or more volts. Okay? Now, have you ever heard the term, it's not the volts that kill you, it's the amps? Because it isn't. You can discharge 20,000 volts if there's no flow behind it. It's not going to kill you. Okay? It's the amperage, it's the current that kills a person. It's not the total voltage. Because you're going 8,000 volts, I'd be dead if I got 8,000 volts. No! Because there's no current behind it. You discharge it like that, it's gone, you're equalized, right? Now it's enough to ruin a component, but it's not enough to hurt you. Okay? So it's the amperage or the continued push of that electricity, the flow behind it, that can hurt you, not just the voltage. Because the voltage is the potential, it's going like that, there's no flow to it at all. Okay? So those are test questions, just so you know. You're going to see this later. 3,000 volts to feel it, 6,000 to hear it, 8,000 before you're going to see it on a static electric charge. Okay? We have different ways that we can control static electricity. There are ground bracelet straps that you can get that you strap on and then you clip onto the PC. I have never used one, I'll be honest. By just doing this and grounding myself all the time, I've never ruined a PC. I have ruined a PC before I started doing it. Particularly when I was in the Air Force, our computer work area had shag carpet. It was pretty stupid. So I had on more than one occasion times when I saw that, and I was like, crap, I should have touched the power supply. And I didn't. So I walked across, I'm just walking this far across the room, I don't think about it, and then I did. And anyway. They have grounding maps and stuff sit on that. The sound system downstairs is on a big grounding map that's plugged into the wall. That the idea of that is that it dissipates all static electricity too. And then we have shielding bags, the electrical components come in. The idea of those is that it protects them against any static electric discharge until it gets to the point where it's going to be, because that's what these are. These are basically anti-static bags that protect those electrical components. We make sure the power supply is unplugged, hold down the power button, and touch the power supply before we work on anything. Never broke it. When we look at the plugs in a wall, there is a neutral one, that's the big one, if your house is wired right. If your house is wired right, you can't trust that it's wired right unless you did the wiring yourself or you've looked inside the wiring. The big one is neutral, the little one is hot, and the one in the bottom is ground. Okay? If you haven't pulled open an outlet and actually looked, don't trust that those things are all hooked up right. That's why they always say if you're doing electrical work, throw the circuit breaker. Because if it's hooked up right, and I have the switch off, I technically would know that if I touched the white, I'm not going to get shocked. Okay? But if it's wired up backwards, which it could be and still work, then I'm going to get shocked. Yeah?
Hey, this is Mr. Riley. I broke my literature page.
Okay, I'm sorry. I'm in the middle of the class. If you send me an email, I will take a look at it again and see what happened. Okay. Okay, so we want to make sure those things work before we just trust it. The neutral is just one going to ground. It's connected to a big, huge pipe down in your basement that goes out of your house and goes in the ground. It's where any overvoltage goes to, any short goes to. Houses back in the 18 and early 1900s didn't have grounding wires at all. They just had a hot and a neutral. In fact, some of them didn't even have a neutral. On my knob and tube wiring, the wire just comes in one, goes out the other. Comes in one, goes out the other. It's a big loop of electricity. They don't just come out to individual outlets. So that's why you have to be careful whenever you're working an outlet. That neutral or a ground plug is important when it comes to electrical components, because if it doesn't have a ground, then it's way more likely to get ruined if there's any kind of a voltage deviation of electricity. If there is a ground, which is why all PCs have wires that go to ground, okay? If there is a ground, then a lot of times if there's a voltage deviation, it just goes, the power supply just sinks to the ground. And if I have a surge protector, it goes to ground. But if I have outlets that I go and put those little adapters on so that I can only plug into a 2 outlet, if you have a house like that, you need to realize you have the potential of ruining electrical components really easily, okay? Which I have done. Stereo and my home entertainment system. This is what a grounding strap looks like. In this case, he's grounded to the power supply with the strap, and then this looks like it's plugged into power. This is a one plug. Basically what they do is they have a power cord that these are not even there. It's just the grounding thing. So the PC is plugged in to the ground. It looks like it's still plugged in, it's using, but it's not. It's a wire that these are taken off of, and just lets you keep your PC grounded when you're working on it. And that's the same thing here, grounding wire. It looks like a plug is plugged into the wall, like the one downstairs on the PA system, but there's no electrical plugs there. It's just the grounding wire plug that comes to the wall. And if there is wires there, they actually don't go to anything. It's just a plug. I've had ones before that I was like, what? They're just metal plugs. That's the anti-static thing. So we got our power supply, and we got AC coming in. And our power supply works as a rectifier, and it's a hold on, can we think of the word? It's a gosh, just remember it. It's voltage. Let's see if we have a next slide. Oh my gosh. It's a when I'm not thinking about it all, it'll come back to my head. So what the power supply does is it converts AC to DC, it changes AC to DC, and then it changes the voltage from that 110 down to the voltages that we need. The voltages that we need are 3.3, 5, and 12. Different plugs put out different voltages. Okay? So the little tiny one puts out 5, all these put out 12, and this one puts out 3.3. The biggest plug puts out the lowest voltage. It goes straight into the motherboard. It doesn't need to be high voltage. Which doesn't mean that it doesn't pull a lot of amperage through it, but the voltage is low. Okay? So the motherboard uses 3.3. Anything that turns pretty much uses 12, and the little extra one from the floppy drive, which is usually not used much anymore, is only 5 volts. Okay, but the voltages that come out are 3.3, 5, and 12. 3.3, 5, and 12. My brain's just not letting me find the vocabulary word I was looking for. Okay, so when we have different plugs, you're going to have this on your test. The big one's 3.3 volts. This one are both 12 volts. The one that plugs into your motherboard and the one that plugs into all the components. And the little one is 5 volts that hooks up to floppy drive. That one's an old 18 volts. I should change my picture on this one. Need that. Okay. I'm going to have you read this stuff later. We're not going to read anything today because I want to talk today so you guys can read and watch videos the next class, because I want to go out and I want to pull power supplies and test some power supplies. We're going to do it downstairs on the ones that we're going to throw away so you guys get a chance to pull and test some power supplies. So I'm not going to do EMI today. We're going to go and do that later. The rest of the class, we're going to go downstairs and I'm going to have you guys see how to pull and test power supplies. Everybody needs a power cord. We can go ahead and stop this.